Hello, this is Mike and we have a new device to repair. Unfortunately, I've already started with the diagnose, my bad. But yeah, I found something interesting which you should not miss, especially when you're on your own hands for short circuits with your first repairs. So this is a nice Asus ZenBook model. One second. UM325U. A really nice device. What a small mainboard, huh? Really small. Okay, so what's the problem with this one? We have actually a no power issue. So the device is basically dead. It doesn't make anything. And in this case, and today, we will simply jump over the usual troubleshooting because I already found out it could be quite dangerous for the board health when I apply power to the board. Because we have a short circuit on the main power rail. Let's zoom a bit in. So this is a quite complicated design. It is a USB-C design. So we have a PD controller which has a control about the delivery of the 20 volts from USB-C to the charging controller, which is I think somewhere located here. So with these special designs, it is a bit harder to find the main power rail, actually. We can, of course, check like before at the various buck converters. There will be often capacitors around. One side has connection to ground, the second side has connection to the main power rail. Yeah, this will still work too, but another thing which you will always find is a coil with two MOSFETs on one side and two MOSFETs on the second side. This is the actual buck boost converter, the so-called buck boost converter. So basically the power from the USB-C ports is coming here, goes through the through the PD circuit, comes to this buck boost converter, will be converted from like 20 volts to, I don't know, what's the battery rated, I have no idea. 10 volts, 12 volts, 13 volts, something like that. And when we finally have the main power rail at the output of, at the drain of one of these MOSFETs here, and when we'll check resistance to ground here, for example, you hear it already beeping. Let's go into resistance mode. Here it's 6.8 ohms, while ground is don't have proper ground here. Here we have proper ground, and here we have our 6 ohms, 7 ohms. So this is very likely our main power rail, which measures 7 ohms. We can check somewhere else. For example, here we have a small controller. We have probably on one side the main power rail, on the second side we have ground. Here's ground, and here's the main power rail, and we have the same 7 ohms. Or we can check here. Here we have the same configuration, two big capacitors, one side is probably ground. This is already the main power rail. So here is ground. Yeah. And here is the main power rail. 7 ohms. Alright. So the main power rail is shorted. That's easy and a complicated diagnose at the same time. because here a beginner would be easily confused or even went on the wrong route. Because normally, when you have a short circuit on the main power rail, you could have the idea to blindly inject 19 volts in the main power rail to see what is getting hot. Yeah, I understand that, but it is basically a bad idea to inject 19 volts into the main power rail, which has a short circuit. And in this case, we don't even read about a full short circuit, but about a partial short circuit, which is very important to notice. Very, very important. Because a full short circuit would be, this 0.4 ohms, alright? But we don't have 0.4 ohms on the main power rail. We have almost 6-7 ohms on the main power rail, which is not a short to ground. It is not a short to ground. This is important. It is a short with another power rail, actually. And this is the case in 99% of the repairs where the main power rail is not straight shorted to ground. You have a short circuit with a secondary power rail then. So, but what should we do now? What should we do now? Should we start injecting anyway? Yes, this would be actually an idea. Very low voltage, let's say 1 volt, to not damage, for example, the APU here, which could easily take the voltage you inject in these cases. Personally, I prefer the multimeter method because it is not invasive, so no harm can be done to the board. So we know the main power rail measure 7 ohms to ground. So we will simply move on and check the other power rails. Here, nothing. Here, nothing. 5 kilo ohms, 11 ohms, 33, 46, 340, 2 kilo ohms, 6.7, 6.6. This is close, isn't it? It is close. And now the magic move. We'll measure resistance between this 6.6 ohms and the main power rail. Right here. And it is 0.5 ohms. So this is a short between the main power rail and this buck converter here, which probably supplies the APU core. 0.5. So what does it mean? It means that the MOSFET, the high side, the so-called high side MOSFET, which is connected between the main power rail and the secondary power rail here, is internal shorted, like internal shorted MOSFET on the in the DC-in area. It's basically the same. It's shorted. The voltage can simply go through this MOSFET without any conversion to a lower voltage. And this is what makes the situation so dangerous for the APU or the Intel CPU or a PCH or a GPU. It's everything. It's all the same. It's very dangerous because the 19 volts or the 13 volts or whatever voltage will simply get into this secondary power rail. supplying the APU. And it is not supposed to be like that. Here we probably expect something like 1 volts, 1.2, something like that, but not 19 volts. So, so what should we do now? We have to find the MOSFET. We have to find the bad MOSFET. How can we do that? Actually, we have where exists a few different methods. Let's check again. So we have a short circuit with this coil. We have a short circuit with this coil. And with this coil, I'm not sure. Yeah, here too. And here? Here not. So we have 1, 2, 3 phases of the APU core. The logical conclusion is that one of these 3 MOSFETs here is internal shorted. So now we could simply remove one after another until the half of the main power rail is restored. Or if you have a thermal camera, you can use a thermal camera, of course, too. So let's see. Here we have our board. Here we have our MOSFETs, and these are actually dual MOSFETs. So 2 MOSFETs in one package. The high side and the low side MOSFET in one package. This is also important to know because we have a different footprint. Here's the second MOSFET and here's the third MOSFET. And I would say we start simply with this one. Good. You see? That's a completely different footprint. We have the phase, the voltage output here. Here we have probably ground. Here we have plus, the main power rail. And then we have here some gate pins, gate. And here actually I'm not sure what this is, but it's not important for our repair. So now after we have removed 1 out of 3 possibilities, we will simply check the main power rail again. Here, for example. So just do it between plus and minus of these capacitors, and we have already kilo ohms. So this was a bullseye. Let's grab another ground point. Yeah, it's fine. Perfect. So, now to the question of questions. Will this board work? Well, the truth is, in 99 of 100 cases, the APU or CPU or GPU will be simply dead. Internal shorted. Nothing to do anymore. Because under normal circumstances, where will be simply pushed too much current into the APU. But we have some advantages here. The first advantage is a charger. It's only a 45 watts charger, and short circuit protection will be triggered here too. So that's actually fine, possibly fine. And since we are curious technicians, of course, we want to know, of course. No? So what can we do now? Can we power on the board like that with this missing MOSFET? In this case, since we have removed high side and low side at the same time, it is actually possible to perform a test. What we are not allowed to is to simply remove one MOSFET in a two MOSFET configuration. Let's say we have removed the high side, then the low side has to remove two. But in this case, we can at least try to power it on, because it should work with the two other phases left. Of course, we are not allowed to apply much load onto this APU, because in this case, the other two MOSFETs will fail too. So testing, yes, but very short, only for picture, without any load. And then we are supposed to shut the board down immediately. Okay? So let's install the board into the chassis. I have probably to put the foil here back, because if we won't get picture here, there is no point to proceed, to continue. Simply no point. The APU is bad or dead or shorted then, and that's the end of the repair. But yeah, in my opinion, there's nothing against to test a very short test and to see what happens. So, USB meter. Good, let's plug the USB-C meter so we can see something, or at least I can see something in addition. Okay, so meter plugged, 19.5, 20 volt, and this is already on. Already on. 600 milliamps, 700 milliamps, and we have picture. Not bad, huh? Not bad. Okay, yeah, AMD Ryzen 7. So, but, as I said, no. We stop here. This is good. This is very good. And now we are free to repair the device. Because this was just the diagnose. It is not repaired yet. So what should we do now? Should we replace this MOSFET here? Yes, of course. But if you want to stay really safe and to prevent this MOSFET to fail again, because it could have damaged the VRM controller, then you should not only replace this MOSFET, but this MOSFET and this MOSFET here too, and the controller too. So all three MOSFETs and the VRM controller has to be replaced to stay safe, so the customer won't come back to you with a comeback job. Okay? Just in case you want to stay safe. If you want to live risky, then replace the MOSFET and see. But it can be that the next time this MOSFET will short out, but this will be the end for the APU. This can actually be. So always be aware. Good. Then we will remove the board again. This one is close near the battery connector. So we will set up the preheater to be able to apply less heat. So when we have to set up the hot air below to, let's say, 320 degrees Celsius. And finally, good. So the controller and the MOSFETs are soldered. So let's have a look. Yeah, how it looks now. Yeah. So let's check the power rails in question. Yeah. Okay, so the main power rail to start with. Mega ohms, which is fine. Let's check at another point. Here, for example. Yeah, this is fine. So what about these power rails? 9 ohms. 5.7. It's because the board is still warm. 5.7. And 6 ohms. All right. So I think it could work. I think it could work. Good. Good. Let's see. So 19 volts, 20 volts. Now it's on. 700, 800. Now it's on. It's not working. No way. Let's try to power it off. It's not reacting on power button. All right. Good. Not good. No, well, we have to inspect it again. Mistakes happens. I've probably done a mistake here, and yeah. Or maybe one of the chips is bad. Can be. Rarely the case, but can be. So yes, I've spent a lot of time to figure out what is going on here. So once again, this MOSFET here shorted out again, and the origin of our issue is probably this missing driver here. I've checked pictures in the internet, in the web, and yeah, this part was soldered in these pictures. So yeah, my job was to find out what it is, and yeah, this was not so easy, to be honest. This is the Asus board, and for Asus there is rarely something available, especially for these yeah, Vivo books and yeah, Zen books, and so on and so on. So yeah, I had no luck with ACES, but I've searched further and finally found an Acer mainboard with the same VRM controller, this RT3663BR GQVW. So and on this Acer board there was a part, let me zoom a bit in, and I found this part, a RT9610CGQW. And yeah, it fits exactly to what I found out. Let me move to the microscope. So this is a RT9610C, and I also found the datasheet, which is here. And yeah, it fits actually exactly. We have the enable pin, which is the VCC pin at the same time, which is absolutely okay. We have here the phase pin, which goes to the phase pin of the DRMOS. Then we have the low side MOSFET gate here. We can check with the multimeter here. Here. Yeah. When we have bootstrapping, when we have PWM from the RT3663, I've checked that it connects to pin 3, somewhere here, here. When we have ground, of course, when we have the low side gate, when this is the high side gate. When this is the high side gate, this is the low side gate, which fits to, has connection to here, yeah? Yeah, alright. Good. So, and last but not least, VCC. So this part matches exactly. Now, we simply have to source it. Top marking is 2Q and a date code letter. Let me remove this. And as lucky as we are, we have one. We have one. 2Q. Not bad, huh? Cool. Very cool. So let's try to remove it. This is a donor board. Good. Here. Perfect. Perfect. Now we need a new MOSFET. Perfect. So let's solder it. But this should be fine. This should be fine. Remove the solder blobs here. Yeah. This looks all fine. So, are we ready for the great final? Ah, what a repair. I don't understand why I always get these hard repairs. I don't get it. I don't get it. It just never ends. Okay, let's see what the USB-C meter says. Okay, acting like before. So this device is still not working. Can you believe that? Can you believe that? Where are my probes? Why? Here we have 5 volts. 0.7. 1.1. 0.6, okay. Nothing. Nothing. No, the cord doesn't come up. Which is strange. I was sure. I was sure it will work, but it doesn't work still. This becomes a nightmare right now. Okay, this is shorted. This appears shorted again. Okay, you know what? We will remove these two again and see whether it boots up by any chance. I had to do that to understand whether this has anything to do with our driver we have soldered there, or whether this is actually a new issue which appeared out of nowhere. Let's plug the charger. No, it's a new issue. It's a new issue. I mean, do we have stable 3.3 or not? Here? We have. We have. And now drops and comes back. Drops, comes back. Yeah, we have an issue with our 3.3 always. But I think my VRM controller is heating up too. Something is happening with my VRM controller. So I was supposed to replace it? Probably. Probably. Now we have this mess here. Power good. Yeah. Power good pin is shorted to ground. On this side is fine. Good. So our PWM controller probably died. So we will replace it another time. Good. Let's check power good pin. Here. Good. Whew. What the exhausting repair. So here was it, right? And kilo ohms. All right. So this is fixed. So now once again, with the combination without driver and without MOSFET, let's see whether something is happening. Yeah, it's turning on now, all right? It's turning on. Good. So now we will solder the good MOSFET and the good driver back. Good. Good. All right. Good. Let's check the main power array. Main power rail is hot. Five volts is hot. This is ground. This is the main power rail. The power good pin. Good. Good. So no idea, another function test. Let's see. Cold enough? Yeah, this should be fine. And is starting. Is starting. Finally. So, will it work now, finally, or not? Still, let's see. And it is on. It is on. 600 milliamps, 800. So what was this sorcery? This was a crazy repair, a crazy repair. Nothing normal. Okay, it is done. I want to check it with operating system and yeah. When I will come back. See you soon.